There are different forms in which the designer can represent that the transfer function, not only the phase variable form. First of all, let us take the case of the cascade form. In the cascade form, we have let us consider a transfer function. Now the transfer function can be represented by the different first order blocks in this case, and then after representing that, let us suppose that we have to analyze first the first order system in this case, and then we find the signal flow graph of the first order system, and then we used with all other systems. Cross multiplying, we get this. After taking the inverse Laplace transform and solving for dci by dt yields this equation. Now the signal flow graph of this is like that. That is, in this case we have the dci by dt equals to minus ai cit plus rit. So we have this rit, then we have this dci by dt, that is the integration dci by dt. We have here the ci, then dci by dt is equals to this. So it is minus ai ci and rit in this case. This can be repeated for all the three blocks of the system, and finally we get the finally observing that we obtain the state space representation of this system. And now from this state space representation, some observations can be made. Now in this case you will see, now when we compare it with phase variable form that we have discussed previously, that in the phase variable form all these terms were on the this third row. However, it is diagonally. That is, in the phase variable representation, the coefficients of the system characteristic polynomial appeared along the last row, whereas in our current representation the roots of the characteristic equation, that is poles, appear along the diagonal as shown here. Now the second form that we discuss is the parallel form. And now in the parallel form, if it is represented in the parallel form, then the matrix A in this case of the state variable is purely diagonal, provided that no system poles is the repeated root of the characteristic equation. Now in this case, let us consider that a transfer function, we obtain the partial fraction of the transfer function, and we write the equation like that. Now in this case you see that Cs is the sum of these three equations, which can be implemented parallelly. That is, it is sum of the these three equations, so these can be implemented parallelly in the signal flow graph as given here. And after writing the signal flow graph by inspection, we can obtain the this state, that is we obtain this in the state variable form by looking at the signal flow graph in this case, and finally the final result will be like that in this case. Though this representation gives the parallel that is matrix system, matrix A. So what is the advantage of these matrix? That is, what is the advantage of this form? The main advantage of this form is that each equation is the first order differential equation in this case. That each is the first order differential equation of one variable, and we would solve these equations independently, and these equations are also known as the decoupled. Coming to the third form. In the fourth form, first was the phase variable form. In this form we have the repeated roots in the denominator. Which is given as this. Now representing in the partial fraction expansion, which is given as this in this case, and after that the signal flow diagram can be obtained in this case. However, in this case this minus 1 by s plus 1 was found by creating a signal flow from x2 to cs in this case. So this can be formed by creating a signal flow from xs2 to cs in this case. So inspecting this signal flow graph, we obtain the state equations in this case, and the output equation in this case, and parallel form can be represented like this. Now in this case, though the system matrix is not diagonal, has system poles which are along the diagonal. However, off diagonal elements in this case of the repeated root, which is actually due to the repeated root, and it is also known as the Jordan canonical form. Now third one is the controller canonical form. Now the controller canonical form can be obtained from the phase variable form. It can be obtained from the phase variable form by ordering the phase variable in the reverse order. That is, we obtain the phase variable form, then order in the reverse order, we get the controller canonical form. Now it is known as the controller canonical form because it is used for the design of the controller, which we study in the subsequent lectures. Now let us consider this transfer function. Now with this transfer function, we obtain the phase variable form as given here. That is, we obtain the phase variable form. It is represented by like that. That is, we have 9, 26 and 24. 9, 26 and 24. We write here the coefficients here, and 1 here in this case, and 2, 7, 1, 2, 7, 1 here. So we got the phase variable. Now renumbering the phase variable in the reverse order, that is, we renumber it. That is x3, x2, x1, 0, x3, x2, x1 and x3, x2, x1, and again rearranging this in ascending numerical order. Now we rearrange it in the third step. What we do, we rearrange it in the ascending numerical order. That is, now all the terms of this we take along with that to this we rearrange in the ascending numerical order, and as a result we get this form. Now this form is the controller canonical form is obtained by renumbering the phase variable in the opposite order, as we have observed this. Also, the phase variable form and the controller canonical form contain the coefficients of the it contains the coefficients of characteristic polynomial in the bottom row and on the top row. That is, one is in the bottom row and other is in the top row. Now the system matrices that contain the coefficients of characteristic polynomial are also known as the companion matrices of the characteristic polynomial. The phase variable and controller canonical form result in the lower and the upper companion system matrix. Companion matrices have the coefficients of the characteristics polynomial in the left or the right column. Now next we discuss the observer canonical form. Sorry before going that, we draw the this signal flow representation of that. In the signal flow representation, you have seen that here we have the phase variable form, that is x3, x2 and x1, x3, x2 and x1. Then we convert it into this controller canonical form, that is x1 is replaced by x3, then x2, x2 and x3 here, x1 with x3 we can see. By using this we can convert this form into from phase variable to controller canonical form, and then controller canonical form to this phase variable form. Now come to this observer canonical form. Now observer canonical form is used to design the observers that we will discuss in the subsequent lecture. Now takes this same example. Take the same example that we have taken in the previous case also, that is this one, and now divide it by the divide with the highest power, we get this form. Then cross multiplying, we get this form, combining the terms of like powers of the integrator, that is 1s, 1 by s square and 1 by s cube, and then it can be represented by that 1 by s in the bracket we have 1 by s. When we multiply this is we get 1 by s square, and then we 1 by s and 1 by s cube. So finally we get that. Now we convert this into signal flow graph. Now first of all we start with the three integrations as we have done in the previous case also, that is x1, then sx1, x2, sx2, then x3, sx3, and input rs and output cx in this case. Now in this case we will see that from the first term we observe that rs and 9 cs, actually by integrating the rs and 9 cs we get the cs. That is, by integrating rs and the 9 cs means that we integrate this rs minus 9 cs, integrating one time we get cs. Similarly 7 rs 26 cs, 7rs and 26ts when integrated 2 times, this one and this one, we get cs, and similarly 2rs and 24cs, it is integrated 3 times, then we get this form. And by using the signal flow graph, we obtain these state equations here like that, and the output equation also, and metric form, in the matrix form it is represented by this equation, that is these equation and these equation, it is represented by these equations. Now from this some observations can be made. Now this form is similar to that of the phase variable form, with the exception that in this form we have this coefficients in the first column, and in the phase variable form we have the third row in this case. Also notice that the observer canonical form has a matrix, that is the transpose of the controller canonical matrix. Now we have the controller canonical matrix, so this controller canonical matrix, so it is the transpose of the observer canonical matrix in this case. Also we have this observer canonical matrix, we see that this is a B matrix 172, this is a B matrix, B vector, that is the transpose of controller canonical C vector, so it is a transpose of controller canonical C vector, and also is C vector, and in this case also the C vector, it is actually the it is this C vector is the transpose of controller canonical V vector, that is transpose of controller canonical B vector in this case. So thus the system is described by so we therefore say that these are duals of each other. Observer canonical system and controller canonical system, these are duals of each other, and system can be represented, if the system can be represented by A, B and C, then A dual equals to A transpose, B dual equal to C transpose, and C dual equals to B transpose in this case. Now in the signal flow graph, the dual can be obtained from that of the original by reversing all the arrows. It can be obtained by reversing all the arrows, that is we have to reverse all the arrows in this case, changing the state variables to their derivatives, we change the state variables to their derivatives and vice versa, and interchanging the CS and RS. So that is how in the this signal flow the dual can be obtained, that is AD equal to AT, BD equal to CT, CD equal to BD, BT, and also in a signal flow graph we reverse the arrow, changing the state variable to their derivatives and interchanging the input and the output in this case. Now let us discuss the state space representation of the feedback system. Let us suppose that we have the feedback system. Now in this we model the forward transfer function in the we have to model the forward transfer function in the cascade form. Now from this transfer function we get that it has the gain of 100, pole at -2 and -3, and 0 at -5. Now using this we implement, as we have done in the cascaded case, we implement in the signal flow graph as given here. Now after that what we do, we represent it, that is we include the feedback path also in that, because the feedback path is here as -1 in this case, and input RS is there is equals to this one minus this, so input is also implemented here and feedback is also implemented here. Now observing that signal flow graph, the state equations can be obtained as, in this case the state equations are, that is x1 is equals to x1 dot is equals to -3 x1 plus x2, then we have x2 dot which is equals to -2 x2 plus 100 R minus C. Now in this form we have to find out that what is C in this case. Now from this signal flow graph, the value of the C in this case is 5x1, so it is equals to 5x1, that is from here we see that it is equals to 5x1 plus x2 minus 3x1. So this c is equals to 2x1 plus x2. So we substitute this here, we substitute the value of the c, and finally we get the state equations, and after getting the state equations, the final state equations can be represented this and this. Okay, now we have the different form of the different forms in which we can represent any transfer function other than the phase variable form. So here we have the transfer function, that is s plus 3 divided by s plus 4 into s plus 6. So we represent it in different form, that is, first we have to represent it phase variable form, then parallel form, then we have implement it in the cascade form. It depends upon the type, on the designer, that what type of form he prefers. Then we have this controller canonical form, and then we have the observer canonical form. These controller and observer, these forms are actually the duals of each other. So in this case, it is transfer function is represented, then signal flow graph is represented, and state equation is represented for comparison of the different forms, so it would be easy to differentiate. And now here we have the controller form, and it is the observer form. Now after this lecture, we will discuss the this similarity transformations. Thank you very much for this.